PowerPoint, Matthias, not like the big slide. See the whole PowerPoint screen.
I know. Yeah. Hold on.
Okay. Oh, perfect. Awesome.
So thanks everyone for coming to this session. We are happy to have Matthias Christandl telling us about two tensor optimization problems from quantum information.
All right. Thank you very much for the invitation to speak. I have to apologize maybe on at least 3 accounts. So first of all, I didn't make it to Berkeley. It's really a pity, but I guess another Greek letter is haunting the planet at the moment. The second thing, it's kind of like my 15th hour awake and going, so I'm not as sharp as I would hope I'd be. And I guess the third thing really is I'm going to tell you about 2 pieces of my work, and you will see at the end of my presentations of these 2 problems how they're connected with actual optimization problems. But I think there is many connections that we've seen already to Frank's talk on Monday, and also Peter's talk on representations, etc. Just before, and then this sort of like second part is really a prelude to Fulvio's talk. Actually, I don't know, has he already spoken or is he?
No, not yet.
No, not yet. Okay. Yeah, I'm really sorry. I can't participate in the program. It's kind of like at midnight party over here when it's running. So I'll do my best to be as much as I can here. Okay, so let's get going. Oh, here's another apologies. I usually have more pictures in my slides, but I did sign this document about the recording, and after having signed it, I thought I'll take some of those pictures out. I was not sure about the copyright there. Okay, here we go. Okay, I'll give you some introduction, and many of you have seen it already, but I'll do it anyway. Then I will tell you about quantum entanglement, and then some stuff. This is stuff I started with Michael actually back in Zurich, and this is a. I hope you enjoy this little wooden thing that I made out of wood. Well, I made it out of wood. And the most difficult aspect of it was actually to hold the lamps so it would cast the 3 shadows. All right, and then I'll talk. Well, okay, hold on. It's not so good. What's going on? And then I'll talk about quantum matter, and this is a second optimization inspired optimization problem that I'll come to. Okay, quantum entanglement, and then quantum matter, 2 problems from quantum information theory, very prominent problems, and I think I hope they're of interest to the community. Okay, so my intro really connects now quantum information to algebraic geometry, and I want to spend some time on that to get that connection straight, and then once we have that, we can play with it. Okay, so let's just do that. Let's get going. So we all, if you're not from the quantum world, you like to think about bits and bytes, I guess. But here we have 3 bits. I indicate them by levels. It's like a level system, and they can be all down or all up or in any of the other 8 states. In quantum mechanics, we think of these 8 states as 8 vectors in a complex vector space, and thus naturally quantum systems can be in superposition, so they can be other vectors. They can be linear combinations of these vectors. Okay, so this is just a way to think about it, and to just take superpositions of zeros and ones. It's somehow very strange, and it's not the same as taking a certain thing with a certain probability. Yeah, so here is mathematically, you choose a basis for a 2-dimensional vector space, and then you take the 3-fold tensor product and you manufacture a state in it, or you bring your system, and it's indeed possible, people have done that in the laboratory, to produce descriptions of quantum systems that are all down and all up with a 50-50 superposition. So And these things are really done routinely now in laboratories around the world. And I think if you see what is happening to quantum computing as a research field at the moment, the fact that we can do that, the fact that the quantum states I'm writing down now are actually being able to produce in the lab, this is somehow what is the difference between now and 20 years ago, and this is what's driving all this excitement. But in many problems in quantum information theory, these complex vector spaces actually we don't need to endow them with an inner product. So normally in quantum mechanics, it's the inner product is very important. And that has to do with connecting it to probabilities, and it's known as the Thebourns Rule. And so in quantum mechanics, if you open any book in quantum mechanics, it will start by saying, well, let there be a Hilbert space. Okay, every physical system has an associated Hilbert space, but Hilbert space means it has an inner product. And so if we, for some problems, the inner product is less important than for others. So if we look at problems where we can neglect the inner product, then it's just vector spaces. So we just have the tensor product of the vector spaces, and then I'd like to call it a tensor. So I just have an element, and it's the tensor product of 3 spaces. And instead of 3, you could look at 2, or you could look at 1, or you could look at many. 3 turns out to be a nice number because 2, the case of 2 is fairly simple to handle, and in the case of 3 is sort of like the simplest non-trivial case. So we'll just write down T in a basis. So I choose a basis EI for my first vector space, and a basis EJ for the second, and a basis K for the last. And I drop the symbol for that makes it different, but I could choose different bases for this vector space if I wanted. And then I have the coefficients, so Ti, J, K, and I call that my tensor. Now, oh, okay, I noticed it's actually very slow to transition, it seems. I have a problem with the slides now. Ooh. Sorry for this. There's some problem. It was very slow, so I hope it didn't. Okay, so I'm back here, and I'm still hoping to. Ooh. Okay, I don't know what the problem is. Okay, I'm a little bit stuck. I'm sorry for this now. I have to go out of the slideshow. I don't know why there's a problem with the speed of the slides. It doesn't want to transition as I want it to.
Can you try closing any other programs you might have open?
Yeah, I can close Zoom.
Is it is it actually slow on your end?
Yes,
well?
yes, it was actually slow on mine. I'm closing Microsoft Word. Maybe that is the culprit. Okay, I apologize for that. I'm closing one after the other. Now most of it should be closed. Okay, I'll continue. No, I think, yeah, okay, it comes. Okay, great. Let's see. Otherwise, I don't know what to do. Okay, so there is some special states, and we have already seen the 000 plus 111 state, but I can do this also for R levels, and I can take the sum over the first R. Okay. Now, in quantum mechanics or in any physical theory, the important thing is not only what the states of the system are, but arguably that I want to compute on them. So what do I do? What I compute normally on is kind of like, for instance, a bit flip or conditional bit flip, etc. And in quantum mechanics, the same happens here then, right? It's just it's represented with a nice operation on my space, with a linear operation on one of the factors. If I do, say, operations that are local, okay? So if I just on the first quantum bit, I do a bit flip, then it will just swap E0 and E1, for instance. Okay, and this is the way I'm making transitions in my system. So that corresponds to applying the matrix 0, 1, 1, 0 to the first factor, for instance. Okay, this is not going well. Maybe I can. What do our technicians say? Here's what I'll do. I will just move to do in PDF. Is that okay?
Yeah, PDF is
Okay,
fine.
I'm sorry for that. I'll stop sharing. I'm sharing PDF now. Then it doesn't have the drop down, of course, but I hope it's still okay. It's better than having those hiccups the whole time. All right.
You can still enter a slideshow. Okay, that's fine.
I think we're going like this. I think it's the easiest now to do that. Okay, we're here. Okay. Okay, so this all leads us to a notion, this operations on a quantum system. It leads us to a notion that has been known since the 80s. It's a notion on tensors called restrictions. And it was sort of rediscovered in the context of quantum information theory. And there it has this sort of very strange name, local stochastic operations. And it's a pre-order on the tensors. It says that T is bigger in this order than T prime if I can act locally, so on the individual spaces with linear maps A, B, and C, such that I obtain T prime from it. And this is a standard notion now, and in the quantum context, it corresponds to doing quantum operations, doing measurements locally, and to post-select. So it's maybe a strange notion, but it does feature in these two optimization problems later, especially in the second one. It turns out to be a very useful notion. Yes. Okay. So here's an example of understanding in which way the just for my case of C2 tensor C2, how what this order does with all the possible tensors. So it brings them in some order, and you see that actually there's 6, 1, 2, 3, 4, 5, and 6, and there's also the null tensor. These are 6 tensors that have the property that they are characteristic states for the orbits under this restriction. Okay, so if you under restriction are restriction imposes results in an equivalence relation, namely if one restricts to the other and the other restricts one, right? And then we say two are equivalent, and so any tensor in 3 qubits is equivalent to one of these 6 states, one of these 6 tensors. And in addition, you have this hierarchy among them. Okay, so if you start here with the middle one, which is called the W state in quantum information, and then it can restrict to this state, for instance, and you restrict by applying a map. For instance, you put on the last part here, you apply the map C that has E1 in the kernel, okay? And then thereby you kill that term, and then you're left with these 2 terms. And then you apply this bit flip that we had just before that swaps E0 and E1 on the first one, and suddenly you are left with E1, E1, and plus E0, E0, and on the third component you have E0. So this is a way of going from the W state to these to this state here, which is actually you see it's a little unit matrix on the first 2, and then quantum computing, we call them Einstein-Podolsky-Rosen states, since they played an important role in the paper from 1935 by these 3 authors. So in this way, actually all of these 3 qubits can be classified, and of course this classification from a mathematical point of view was already known in the 19th century. So this restriction, if we now connect to talks that we've already seen, then here is the definition again of restriction, and we have this equivalence notion. So T is equivalent to T prime if it restricts both ways. And you see that if now the dimensions are the same, then actually that notion is equivalent to having to the orbits under the GL action be of the tensor T and the tensor T prime being equal. Right? So you look at T and you look at all of the things that are equivalent to T, and you look at all the things that are equivalent to T prime, and this way you can decide, or this way you can see the classification of restriction, of this restriction operation, actually as a orbit classification problem. And it's a little bit more than an orbit classification. It's really an orbit classification and understanding the relations between these orbits and how they relate. And that is why I showed you the graph from before. Now, there was something that I hadn't told you before about, and that is that that this operation of restriction is not closed in a sense. So what can happen is the following strange effect, namely that now, if I'm going back to my classification here, that if you see here up here, it says this 0, 0, 0 plus 1, 1, 1 state, there is an error to 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0. But one thing that maybe many of you know is that the so-called tensor rank of this W state is actually 3. And so the tensor rank cannot increase under restriction. So how is it possible that I put an error here from something that obviously has tensor rank 2 to tensor rank 3? And the reason I put this error is that it's actually possible to do this transformation approximately. I want to show you briefly how that goes. You manipulate, so you send E0 to E0 plus epsilon E1, and then you send E1 to minus E0 on all of the 3 factors. And so this one here is equivalent to this, which I call the GHZ state, the Greenberg-Owen-Seilinger state. But now you do an epsilon expansion, and you see that in 0th order, E0 tensor 3, the 0th order is vanishing. So in first order, you got something epsilon, and then suddenly you got this thing that has rank 3. So it sort of like emerged out of this limiting procedure. And therefore, and here is actually a kind of nice illustration. If you think of the left-hand side here, right? If you think of all of the things that are product as this curve, right? It's sort of like a cubic curve. If you think of this cubic curve here, and then this difference of these 2 points on this cubic curve. So the red point is E0 tensor 3, right? And this point here is E0 plus epsilon E1 tensor 3. And then what you do is, so then somewhere on this line, okay, somewhere on the secant, we have just the sum or the difference of 2, so somewhere on the secant. And what happens now is that when we take the limit and we take epsilon to 0, right, we move here and so on, and then it crashes. So algebraic geometry would actually say it crashes in, so Fulvio would say that. It crashes into the E0 over here. And then what happens is that the resulting state, it lies on the tangent. So it's not the secant, and so therefore it doesn't have rank 2, but it's a tangent to this curve. And so this gives rise to a notion of degeneration. So T degenerates to T prime if I can find a sequence of tensors, so in parameterized by epsilon, that actually approaches T prime, such that T restricts to T epsilon. So it's really the closure operation. I can from T go arbitrarily close to T prime. And so what we see then is that deciding degeneration is actually classifying orbit closures and their relations. And therefore, orbit closures are G invariant algebraic varieties, and of course that's nice. We can use the machinery from algebraic geometry now to attack this problem, and people have done so, and as I mentioned already, for a very long time. All right. So you could, for instance, say T doesn't degenerate to T prime if and only if there is a polynomial, a G covariant polynomial, such that it has different values on this tensor. And an example is, of course, now the backwards way. Okay, so if we take the Cayley hyperdeterminant, course, Cayley, that's a long time ago. And it evaluates to 0 on this W state, but it doesn't evaluate to 0 on this GZ state. So we cannot actually go up here. Now, if we, and this now, I think now leads us to a full understanding. And for higher number of particles, higher dimension, really, we don't know how to deal with this. And I think this is sort of, I want to highlight that it really is intractable, right? So you just go a little bit higher and it feels intractable. Yeah. Now, in quantum information theory, what we like to build, and I think it's really like a general computer science theme, of course, is we like to understand resources. And in this particular case, it's the resource theory of tensors, where you think of the tensor as a valuable resource, and you ask yourself, how does this resource transform under restriction? So restriction is the free operations under this resource theory. And I have a unit, it's kind of like a unit money somehow of counting. And then of course I have a price. I have a price for the tensor. How much of this unit R do I have to pay for my tensor T? How much does it cost? And this is typically known as the rank. Maybe somehow more natural would be to take the logarithm. Okay, so you'll see that later. All right, so if you think of the tensor as expressed in quantum bits, and you look at a large system, and you think it's like the analog of bits, right, in your communication infrastructure, you would usually pay per megabyte, right? You wouldn't pay per number of levels, so per 2 to the megabyte. So it's more usual, more natural actually to look at the log rank and the lob subrank. So subrank is what you get when you sell it on quantum eBay. Again, you take your tensor, you sell it, and how much of this unit tensor do you get back when you sell it? That's the subrank, or the log subrank. It's the money you get. Any questions at this point? You're welcome to ask questions. I hope you can hear me.
Yes, we can hear you.
Okay, great. Okay, so that was the prelude. Quantum entanglement, how to test for it, how to measure it. Okay, so so we're basically in for understanding how much tensors cost and how much we get for them when we sell them, and we call that entanglement usually. Okay, so here is a way of understanding it. And one way goes via understanding these polynomials better, right? So you say, okay, so these are all closures of gene-variant algebraic varieties. Let me use polynomials to distinguish them. And these polynomials, they come in different types, and these types are indicated by so-called highest weights, if you think of the GL representations, or you can think of them as Young tableau, or Young frames, if you run the whole thing once through Chauval duality, you have this duality between GL and the symmetric group, so you can take either viewpoint. So since we have a triple of GL, whatever comes out will be a triple of Young diagrams to understand this. Okay, here's Chauval construction. Okay, it's kind of very nice. You take CD tensor N, and then CD tensor N, you see, has a very natural action of GL, or also of the unitary group that Peter used, and is a diagonal action, so all of the particles are rotated in the same way, and also it has a symmetric group acting, and the two are maximally commuting, so there's nothing more that commutes in these two, and so we get this really nice one-to-one identification of them. So what then happens is, what you can do is you can say, well, okay, so let me look at these parts, okay? So let me kind of like look at the irreducible parts of my tensor in some sense. So I take a high tensor power, and then I'm projecting this tensor. I'm just looking at this submatrix, gigantic submatrix if you want, and I'm asking myself what this is and what properties it has. And then we can do a first relaxation, namely we can we have this if and only if up here, right? There is the G covariant polynomial, but if we don't look at the polynomial itself, we look only at the diagrams, because for a given diagram, there are many polynomials, okay? So many any polynomials for a given diagram. So we're not going to look at all the polynomials. We're just looking at the diagrams, and we just ask, is there a lambda? And this is, it's sort of a relaxation, right? This you could have called an F, you could have called an obstruction, but now, of course, these here are occurrence obstructions. So does the lambda occur in geometric complexity theory? Like that. Okay, and we do another relaxation, and this brings me to a work that I've done Michael time ago. Namely the concept of entanglement polytope. So it's another relaxation because we're like saying, okay, well, you want to look at this diagram? Well, why do you only look? Let's actually only look at the length of the rows. Okay, the ratios of the length of the rows. So we normalize everything by the total number of boxes, and then instead of the diagram 4, 3, 1, we get this 4, 8, 3, 8, and 1, 8. And then, of course, you see if I double the row length, I'll get the same point here. So it's another relaxation. I'm just asking, is there for some number of boxes, so given such this is a probability distribution, of course, given for a probability distribution, is there some number of boxes such that, this is non-zero? And then it comes to first surprise. So the first surprise is that, that if you're given a tensor, and say you're given a tensor like the GZ tensor, so maybe one thing to remark, right? It's clearly GL invariant, this notion of whether or not there is. So for every orbit, right, and actually orbit closure because it's for degeneration, for every orbit closure, there will be a set, right? There will be a set of these probability distributions. And a big surprise is that this set of probability distributions is actually forming a convex polytope. And here you have the 4 convex polytopes, or maybe, well, what is it, 6, right? 6 convex polytopes, because to each entanglement class that I had shown you before, there corresponds this convex polytope. And here is the first one, that's the biggest one. It's also called the Kronecker marginal polytope. Then the next one is this W polytope, which is kind of like a part of that, you see. And you remember the W lies in the closure of the GHZ. So the corresponding polytope should also be contained in this one. And then these the Einstein-Podolsky-Rosen things here, they each form a polytope. So there are 3 lines, these are each polytopes, and then of course the product state is also a polytope. All right. So these are entanglement polytopes, and they have surprisingly a dual characterization. And this dual characterization is illustrated with my little wooden figure that I built. If you think of the tensor, and now I use T prime here as my tensor. If you think of the T prime as the as the wooden object, then the 3 shadows are sort of like partial information about it, right? So, and I can ask, so given any wooden structure, I can ask myself, which triple of shadows do they cast? And given 3 shadows, I can ask, is there a wooden object that casts those 3 shadows? I guess that's, what you have also in medical imaging, that you want to, you get a bunch of shadows, you want to go backwards. And this also we want to do in quantum, right? So we're given, or we have this tensor, and we ask ourselves, which 3 shadows does it cast? What do I mean by a shadow? A shadow is basically, for us, it's kind of like a property. So I have this 3-particle quantum state. It's a property that is only dependent on one of the particles. And so in this particular case, it just means that, okay, what I can do is I can only look at that part. I'm doing that by grouping all the others together. So I have 2 parts, one versus the rest. And actually kind of like the one versus the rest, this will actually tell me, it's all the information I can extract from this one particle. And what is this information? The GL invariant part of that information is the singular values of the map that goes from here to here, and then I square the singular values. And actually, if I normalize my state here to be normalized so that it has norm 1, then now I sneaked it in a product, of course. Then actually these singular values form a probability distribution. So my shadows for my tensor here are 3 probability distributions. So 1 for A, 1 for the C, and 1 for the B particle. Put your head sideways. All right. Okay. So now, and now you're like, okay, great. So I can take this T and mathematically I can put in a moment map framework. That's exactly what Frank talked about. But I wanted to give you this sort of like parts of the physical intuition of why we were doing that, because also this way of thinking that I was trying to present to you now is also something that generalizes beyond settings, which can be dealt with help of moment maps. So here's a big surprise. Okay, so one big surprise, it's a theorem by Briand that we applied to our particular case then, to this triple GL action case, is that the 2 polytopes, that the first polytope that I showed you before, is actually the same as if you look at the collection of shadows. Okay, so if I give you a triple of shadows for the qubits, then it corresponds to just 1 point in the polytope. And I give you the triple of shadows, so every triple of shadows corresponds to 1 point. I ask which triple of shadows are possible, and they actually don't just form an arbitrary arrangement of points in R3, but they form this convex polytope, namely for this one, and these 3, and so this is actually a dual characterization for the polytope. And actually, we used it. You can use this characterization, and you can use it in order to detect whether something is entangled. So we made a little entanglement test. So if you want to, for instance, figure out if you are Greenberger or Zeilinger entangled, or if you are W entangled, and W is weaker, so you want to show to the world that you built this new machine that has a quantum state that's better entangled than the previous machine that was being built. So all you have to do, according to our test, is you have to show that when you measure locally the particles, you are the image of that point is not in the blue part. Okay? Then you're like, now you build a really good quantum device, and this is a way to certifying entanglement and the quality of your machine in some sense. Okay. And people have actually implemented it in the lab, and this is really quite nice. So so I haven't really told you now why or why the mathematics is, and I think there were other, we can talk about that later. I want to bring you more of the quantum information intuition, because in quantum information, one thing. When I say quantum information theory, one thing is that it includes the words information theory. And that is, of course, going back to Claude Shannon in the 1940s, and it's really the backbone of everything we're doing in the internet these days. So what is the basic model of information theory? It's that I have a source that spits out some data, that then you have an encoder that encodes the data such that you can maybe transmit it, or you can store it, maybe put it in storage, and then you decode it. And what Shannon realized was that you could do much better than that if you don't look at a source alone, but you look at many executions of a source. It's a bit like when I'm speaking, I'm having this train of symbols is coming out, and I'm doing an encoder on a block, on a big block length. I'm doing an encoder that takes a whole block, and then I'm storing that, and I'm willing to tolerate a small error. And then I can decode actually, but I used the storage cost is much reduced. The storage cost only corresponds to the Shannon entropy of the random variable that represented the frequency with which certain symbols emerge from the source. So one can dramatically reduce the storage cost, and I think this is one of the backbone really of a lot of information theory. Now, in the quantum world, this point of making sources, it's really the same. Instead of a symbol written on a piece of paper, it's spitting out a quantum particle in a quantum state. And the model of having an IID distribution, like here, an independent identically distributed source, is really in the quantum information realm, the tensor product that connects quantum states with the tensor product. So, I wrote it down for general field F. Okay, so F is now the complex numbers again. So if you think of now, right, so independently sampling first T first a tensor, right, or tensor is now a triple of particles, and then independently having a triple of sources that spits out another tensor T prime. We have to, that's a very natural operation. It's really the one that, every experimentalist every day in the lab does. Every quantum experimentalist, whenever they press the button, and if they press the button of the machine independently, independent copies come out. So let me illustrate how this tensor product now works in some ways, and I'm sure many of you know this, but I actually thought it was kind of fun. This Q is the symbol for our mathematics center here in Copenhagen. So if you and I'm illustrating this now with a tensor with just matrices, just a tensor of two spaces. And so I have this little matrix which is blue, black, yellow, and green, and I tensor it with this Q. Well, what happens? Oh, the colors don't seem to be perfect. Maybe that was the transformation. Okay. Well, you see what it should be. It just duplicates the Q and it gives it the corresponding color from over here. And now when we have tensors like we had before that are three-dimensional arrays of numbers, then if I take, for instance, a pair of glasses and I tensor it with this unit tensor here, which is has something on the diagonal, then you see that I just get the glasses on the diagonal with a certain color. And it's sort of also interesting to do it the opposite way around, right? So if you think of this and then you tensor it the other way around, it actually looks kind of different, but this is of course the same as that, just up to writing it a different way. Okay. All right, any questions to tensor products and how I illustrate it? I hope there's no copyright on these classes. I have to check it. Now, what is interesting is this IID idea, right? So I do independently and identically distributed random variables. I wouldn't really think of it as fractals, right? But if I'm doing this with my tensors, then 1 goes to T tensor 2, T tensor 3, etc. And I think of the T tensor 2, right? It's 3 particles and 3 particles, but I don't think of it as 3 particles and 3 particles, but I kind of like when I do the tensor product, I think of the resulting thing again as 3 particles. Okay, so this is just on a bigger space now. Okay? So what happens is that here I had GLD, GLD, GLD acting, and I have here GLD, GLD, GLD. When I combine them, I have the action is GLD squared, GLD squared, GLD squared. Right? If I take the n-fold tensor product, I have GLD to the n acting on the individual ones. So if you do this with matrices, what you actually get is an example is here the Sierpinski carpet, which kind of looks nice. And I couldn't find the public domain Menger sponge, but if you type it into Google, there's tons of illustrations of it. Okay, so really it kind of like goes fractal in some sense, and I think this is also a bit mind-boggling that nature is doing that to us. Leading us though to now an asymptotic resource theory. Okay, so all this prelude was now to motivate and to tell you that the n-fold iterated tensor product is just as natural in quantum information theory as it was for Shannon to consider IID random variables. It's really just as natural for us. And so it's supernatural to ask, when can I transform n copies of T into n copies of T prime? And And I can give a little fudge factor, a little O of n here to make the whole theory a little more elegant. The unit's still the same, but you see that now, since I'm asking how can I asymptotically transform resources, I have now a notion of asymptotic rank. Namely, it's kind of like the asymptotic cost. Okay, if I want to buy many copies of T, how much do I have to pay in terms of GZ state? Of course, naturally, right? I would like to take the log of this again, okay? Because it's really what I would have to pay in money. And this is what I would get on eBay again, right? The log subrank of this. Okay, it's a very natural resource theory. And in quantum information, we have looked at many resource theories before somehow one considered, well, we have considered this asymptotic resource theory, but I think it's one of the more natural ones. And Strassen, of course, considered it, and maybe that is what connects me also to Peter's talk and to Frank's talk. I should say that Volker Strassen considered this for the case in the 80s. He considered this for the case where he looked at the case where T prime is the matrix multiplication tensor of 2x2 matrix multiplication, and then here T is the GZ state that I showed you before, this unit tensor. So the asymptotic rank of the matrix multiplication tensor here is really is 2 to the omega, right? So omega again is like log of that. Okay? So it's very natural to take the log of this, and then the matrix multiplication coefficient can be cast is actually equal to the asymptotic rank of the matrix multiplication tensor. Okay. All right, so then Strassen hammered away at this. Okay, so he just he defined the problem and he just hammered away at it. He came up with this nice theorem. The theorem says that that if how am I doing for time? Okay, well I should speed up a little, I guess. He says he showed that functions f that track. Okay, so functions f that are monotone under restriction. Okay, so look at functions that are monotone under restriction, because monotones are usually good ways of finding lower bounds on things, right? So if under some if you well you know that, right? So monotones are the way to get obstructions, and he actually showed, and this is sort of like this is the non-trivial part, that there's a complete set of monotones of a certain structure, and the structure is that these monotones are actually multiplicative and additive. Okay, so he defines a ring of tensors, and these are actually ring homomorphisms, and these are ring homomorphisms that have this monotonicity property. So it's really kind of a beautiful theory of obstructions with a lot of structure, and these obstructions allow you then to say something, right? To understand the asymptotic rank, asymptotic subrank. So here are some examples. Okay, so what's such a monotone ring homomorphism, right? And you all know them and love them. It's matrix rank. Okay, so if you look at matrices, and the matrix rank is such a nice function. It's if you take direct sums of matrices, it adds up. If you take tensor products of things, it just multiplies, just as I showed you. It's normalized. If you put the unit tensor in, it's D. It's monotone, right? The matrix rank of this is 2, the matrix rank of this is 1, etc. Okay, these are really nice examples. So all you have to do is you have to take your tensor. You have to, so all you have to take your tensor, you have to flatten it like I did before, right? So I group 2 of them, like I make this kind of shadow thing, and then you apply, and then you compute the rank. Okay, great. That's one of these are 3 points, right? These are three nice monotone functions, and they're called the gauge points. They're very nice. But Strassen showed for other rings and matrix multiplication, he gave a bunch of beautiful constructions for such functions, but he didn't have them in general. So so in joint work with Peter Frana and Jeroen Zautam, we actually were able to interpolate, if you want, between these extreme cases. And I want to show you, because it's an optimization problem, okay? So it's an optimization problem over entanglement polytopes This is also what Frank talked about. So it's really an optimization problem. What we're doing is, and I want to advocate a little bit for that. So let's say we want to interpolate, right? So we want to interpolate. We want to kind of like take the average of these ranks, right? These nice ranks that I've showed you. And how do I do that? Well, what I do is actually I'm choosing a weighting on how I want to average. So let's just say a third, a third, a third, not to get confused. And then I'm taking, I'm looking at the point in this entanglement polytope. Remember, these points in entanglement polytopes, they're triples of probability distributions. So I'm taking a triple of probability distributions, and what do I do with the triple of probability distribution? Well, I think back to 1940 and I take the average Shannon entropy of that. Okay, so let's just do that. And it's just the average Shannon entropy, what to do else with probability distributions. And then you compute this E, okay? And now because this rank is defined, so we have to take the exponent of it. Okay? So, but what is important is that if you think back of your entanglement polytope, it's really computing a distance to the origin, okay? What's the origin in this thing? It's always, the origin is the points. Okay, so what's the origin? Okay, so let me connect to Frank's talk. Is the origin is, so I guess the tensor, okay, the tensor corresponding, so if a tensor has a corresponding polytope that does not include the origin, then the tensor is in a null cone. Okay, so that's the connection. It's a connection there. But given that it is not in a null cone, or in general, what we can do is we can try to compute the distance to the origin. Okay, so if we try to compute the distance from here, right, we'll somehow, you know, we start here, we're trying to compute, we're trying to get closer to the origin, we get stuck somewhere over here. And we can kind of like wonder how big this distance is. Now what, instead of computing a distance here, what I'm actually doing is I'm maximizing the entropy here. So I'm kind of like maximizing, and the entropy would be maximal if I end up down here, but maybe I get stuck somewhere before. Okay? And how I'm doing that, I have different ways of doing that. I have different ways of doing this maximum entropy principle if you want. I can weight the three coordinates in different ways, namely with my theta parameter. And this way I get a bunch of different distances. And I think these are really interesting distances. And I think in maybe the literature in moment polytopes and so on, what people have considered a lot was Frobenius norm distances. So like squared, basically matrix squared distances. But this here is really different, right? It's a Shannon entropy distance I'm doing. And the question is, of course, how do we optimize over this? And I think this is what I hope you will become interested in as a problem. Okay, well, long story short, the important property to prove is multiplicativity, and I showed you two ways of looking at the tensor, at the polytope. And you know, multiplicativity, you have to prove submultiplicativity, supermultiplicativity. So it's these two characterizations that they are equal that actually give you the multiplicativity. All right, that was part one. I guess I told you everything about these functionals now. And I have a few minutes maybe left to go to part two. Or is there times if you want to have questions now, and I can just say a few words about the remaining part.
Any quick questions now? Maybe go ahead and continue.
Okay. Okay. So the second part is really a tensors now in a different way. Okay. So I'm now going back. Think that what I was really interested in was that I can treat the tensors with a geometry. Now, what I want to import that tool, and I want to use it in the context of tensor networks. And tensor networks are, of course, relevant in different areas of science. They're interested in machine learning, but they're also interested in physics and in order to describe quantum matter. And in physics, typically, if you have some crystal or some crystal structure, you build these tensor networks graphs, right? So you take a graph, and then what people do is they actually place small tensors here on the vertices of this graph. So if I think of a graph, right? So look at this. If you look at this picture, you see that I actually made the graph in such a way that that I want to think of the graph as consisting of a bunch of edges, really, and then of having the vertices at the end of the edges being kind of like grouped together. Okay, so this is how I want to think about it, and then I want to. And then here I would want to look at linear maps applied to these vertices. So if you lay out such a graph, and then you attach a tensor to each of the edges, right? And what a tensor do we associate? Because it's just an edge, I can associate a matrix to it, and then I can apply linear maps to the vertices, and this actually is a tensor network. This is what people call a tensor network. And so one thing that we tried and what you found was a lot of fun was looking at tensor networks where I'm not applying, where the underlying graph is not a graph, but it's a hypergraph. Okay, so I'm starting out from a hypergraph, and on the hypergraph, I can associate different types of entangled states or different types of tensors to the hyperedges, and then apply these linear maps. Because what happens then suddenly is that I get really interesting stuff also on the boundary, because these application of the maps, which is really the operation of restrictions, is not closed. And so what we did was we took a very particular type of tensor network, and we were able to improve on its efficiency in its representation with help of geometric methods imported from algebraic complexity theory. And I think this is a really nice payoff of the connection. Okay? So we could make progress in this problem coming from quantum information theory, and actually it's sort of like an important state, an important tensor network description for the resonating valence bond state. The resonating valence bond state is sort of it's a state that people think is sort of like the model of superconductivity. So for this model of superconductivity, we're able to give a more succinct tensor network description with help of insights from algebraic complexity. And we did that by swapping out the entanglement structure with help of tools. But it's going a little bit too. Let me tell you that aspect. So basically, the numerical code or things that people use in order to analyze tensor networks is usually based on these normal graphs, and we were playing in finding more efficient structures for more efficient representations of this superconducting state. And so all we had to do in the end was transforming certain small tensors on the plaquettes. And so really we reduced the problem to a problem of of understanding the connection between two tensors with help of restriction and degeneration, just as I had introduced earlier. So even though we're looking at a state on this vast network, right, arbitrary sized net tensor network, we could reduce important properties, or did use important properties, by looking at local plaquettes, so at single tensor transformations. And as people know that play with single tensor transformations, they're already very difficult, okay, at this, and we had to employ a lot of algebraic geometry in order to understand this. So really, we were able to understand these restrictions of the states that are relevant and come out relevant in this area of physics. And we're able to make sense out of this approximate, out of going to the closure. Okay, so previously people had observed that when you do numerical procedures and you try to understand tensor networks and to minimize and to find the optimal tensor network representing your physical state, what people had realized that at certain points, you actually kind of like you take off and you go to a boundary, so the problem becomes ill-conditioned. And so we were able to connect that phenomenon in this case to the phenomenon of a closure phenomenon in algebraic geometry. And I think Fulvio will tell you more details about it. But that is sort of what I wanted to give you, home on a high level, that what we were able to do was connecting these tools from algebraic geometry. So we use interpolation theory and all sorts of tools that have been developed in algebraic geometry and in algebraic complexity theory very successfully. And in the end, I think we had our little application that is a new and more efficient representation for this resonating relevance bond state. And with this, I think I'm done. And I want to tell you on the very last slide what this has to do with optimization. And that is because in physics, when you are interested in certain physical state describing a system, what you're really doing is that you start off with an understanding of how the energy in the system comes about. For instance, how the interaction of particles. So here, for instance, I have an energy diagram. So if you think of two hydrogen atoms, and these two hydrogen atoms, you bring them either far apart, or you bring them closer together, or you bring them super close together, right? You can't put them on top of each other, so the energy would be too high. And if they're far apart, then they act like an independent system. So they have a bound state at a certain distance when the energy is small. So how does one compute that? Well, you make a variational, so you have an expression for your Hamiltonian, which is basically a gigantic matrix just. And you minimize, right? You do a variational principle and you minimize over all the possible states. And people do that in condensed matter, of course, with unwieldy large systems. They minimize. And they have found out that it's a really good idea to minimize over these tensor network states. So minimizing tensor network states is really a very important second optimization problem in quantum information. And the work I've just presented to you has to do with the question of how stable are these minimization procedures, or are there things on the boundary? And I hope that at least inspires some thought for people thinking about this. Thank you for your attention.
Thanks. Any questions?
I have a quick question. What are the physics problems you're trying to solve with these tensor networks?
What is the physics problem?
Yeah, like, yeah. What is the sort of physics that you're trying to model with this like lattice, tensors on a lattice sort of thing?
Right. So what people trying to do is basically tensors on a lattice have the property. So the tensors, the tensor networks, they are a very small part of all the possible tensors that are there, right? Of all the possible quantum states I could represent. So because the number of quantum states, or the dimension of your quantum space, explodes exponentially with the number of particles, one has to somehow, in any variational procedure, narrow the search space. So one starts with and one has found out that a good idea is to look at states that only have local correlation. So the correlation is of a fixed size between nearest neighbors, and with this, tensor networks represent a class of states that actually model very successfully the correlations that states in nature have, or that we observe. Okay, so if you this has to do with what we call the area law, that the amount of entanglement in physical states kind of like grows in proportion to the perimeter of an area, and thereby, and these states are a good class. Okay, so.
Sorry, I guess the question is like, what is the energy that you're interested in? Like, what are you minimizing? Once you have this tensor network, what are you?
What you're minimizing is typically it's an energy that is a sum over energies of, say, nearest neighbors in the lattice. Okay, so for every nearest neighbor, you have an energy. So think of electrons or think of other particles, right? They will interact mostly with their neighbors, right? And so you have some energy corresponding to two neighbors interacting, and you just sum up all of these contributions, and that gives you the Hamiltonian, the energy function. So it's a huge matrix in an exponentially sized space, and now you want to find the ground state energy, right? Because you want to understand, you want to be able to draw an energy diagram like I did here for hydrogen. You want to draw some energy diagram that will allow you to say when you, for instance, have a phase transition. So when your system goes from a phase that's akin to like gas into a phase that's akin to a fluid, or a phase that's akin to a solid. Right? Therefore, you are trying to figure out what is the ground state energy. Does that make sense?
Yeah, I think so. I guess you have like some sort of frustration or something where you have a lot of states that all have about the same energy. That's the computational problem. Like you have a lot of dipoles on the vertices of it's a Kagome lattice is what people sometimes call this, right?
Yes. So this was just an example, right? Yes.
Yeah.
But in general, you have in many circumstances you have complicated minimization problems. Yes, where you can have frustration, and even without frustration, right? You run into you might run into problems.
Okay, thank you.
Other questions? I have one question, which is like, when you're optimizing these matrix product states, is there any structure you can exploit, or is it just kind of like still a pretty hopeless optimization problem in terms of like convexity and stuff like that?
What people tend to do is there's maybe two there's two interesting aspects that I think. One is that one typically does an alternating optimizations. You optimize one and you optimize the next, and so on, and you go around in a circle if it's on a circle, or you go around in different ways. This is one way of doing the optimization. I think Michael can probably say more about it in a second. And another very interesting thing I think is on this graph, that if you think of it as lying on a torus, so you take this graph, you wrap it around this way and the other way, then there are other ways of somehow going to the infinite limit. This is called infinite PEPs or IPEPs. So where you contract one ring, and then you contract in sequence on the other direction. But this assumes some assumptions on like invariance, that you have the same, that you don't optimize different ones, but you use the same map on all of the sites, right? So it will put some restrictions on, but it's a different aspect of the problem. But maybe Michael can say more about this optimization problem. I think you've thought more about it.
Yeah, I mean, I think in terms of rigorous algorithms, I think in one dimension, somehow, I mean, there's this method that you described, and then I guess there's some, I don't see exactly who's in the audience, but I guess Umesh and friends have worked on algorithms that I think are approaching practicality in one dimension with guarantees. And I mean, they would construct by some kind of recursive scheme good matrix product state description. I think in higher dimensions, I don't know if there's anything rigorous and efficient. Yeah.
Cool, thank you. Any other questions or from the online audience?
Maybe I have a question, if I may, about this conversion. I mean, you had this nice information theory motivation, and I guess there's lots of variations. You had the little big O, the little O of n That's what we were not worrying about. But I guess another interesting relaxation is if you don't demand exact conversion between resources, let's say with an error that's small and going to 0 as n becomes large. Maybe I blanked and you commented it, but in case you didn't comment on it, maybe you could say a few words. So like, is there also such an approach? Can also define functionals and study like, you know, theories?
Well, okay, so there's so Peter Frana has thought about this problem, and he has done some very nice work on it. But it's not the approximation in the usual information theoretic sense that we know from Shannon, right? It's more quantifying. It's more a deeper understanding of the quantification of the error, and that of course plays in and relates to your work with Frank, right? Because it has to do right. You had these hedgehogs with these functions, and this rate function plays a role in these functionals, right? These generalizations of these functionals, they're defined from the rate function, right? Which maybe we don't know, but they take the properties of these rate functions. And I think it's super interesting work. Yes, Peter Frana's amazing, and this work on the extension of these quant functionals is amazing. I think the question of probability, it's also amazing that it can be cast in this framework. In general, like approximating, that would require us to reintroduce the inner product in a more deeper fashion, and I fail to see how to do that.
So is the thing that Peter looks at, Peter Frana looks at, just to remind myself, is that like, if you look at the probability of these SLC protocols actually succeeding? So yes. Mathematically, it's your description, but you worry yes. about the probability. Okay.
Yes. I see. Yes, it goes in that direction. Yes. Yeah. So it puts that in. Yeah.
Thank you.
All right. If there's no other questions, let's thank Matthias again.
Thanks a lot for having me.
And we come back at 2.
Gonna go home.